today. Couple of quick things before we start lecture. I put up some libraries, if you want to download those, that we're going to use today. Homework 3, I believe, should be out today. Yeah, so I'll start working on that. It'll be due in a week and a half. Project proposals are due on Friday. So I believe I made an announcement about that, but just as a reminder, make sure to get in the proposals by Friday. You only need one proposal per group. There are gonna be a few people working as individuals, but the preference will still be, 2 or 3 people, so that we can try and get as many live presentations as possible. Okay, any questions about any of that? About the homeworks or about the final projects? You can always feel free to email me if you have any questions or issues or anything like that. Okay, so let's go on to lecture for today. So we're going to be continuing our conversation about identification, specifically thinking about strategies for causal identification. And so we kind of work through kind of the mental model, the theoretical, qualitative art of trying to do causal identification, and today we're going to actually look at a couple tools which are going to help us achieve some of those things. Okay, so we're going to look at 3 things today. First, fixed/random effects. 2, differences in differences. 3, instrumental variables. Okay. So the first thing we'll talk about is fixed effects. So fixed effects. So this is a method of controlling all variables. And that's whether or not you observe it. Observed or not, as long as they stay constant within a larger category. Okay. So let us consider something like this. Exercise and weight. So if you exercise a lot, can that affect your weight? What do you guys think? Yes, most people are nodding. What other things might affect your weight?
Diet.
Okay, diet. What else?
Can you say genetics?
Yeah, genetics. Anything else?
Meditation.
Medication, sure.
Height.
Height, great. Makes sense. Age, okay. Anything else?
Race.
Race, stress, great. So, okay, you guys get the point. There's a lot of things that can affect your weight, right? And from a regression standpoint, let's say you only have information about exercise and weight. If I had, let's say I had information from like 1,000 people about how much they exercise on average, let's say per week or something like that, and then I also have all of their corresponding weights. You could probably say something about the correlation between exercise and weight, right? If I were to run like a linear regression, that beta coefficient will tell me something about that correlation. But I might have a little bit more difficulty using that number to describe the causal outcome of exercising on weight, right? And why is that? Anyone? You guys are telling me, right? There's like all these other reasons that could be affecting weight that aren't exercise. So, in order for me to get the causal effect of exercise on weight, what would I need to do? What do you guys think? Let's say these are all the things that affect your weight. How would I?
Including them?
Yeah, exactly. So if you control for these things in the model, then you could say something about this. But it might be really hard to get access to all of this other information, okay? So we will say something like consider weight is a function of beta 1 exercise plus beta 2 genetics plus beta 3 medication plus beta 4 height, and so on and so forth, right? But there are probably an sort of innumerable number of variables related to these individuals that are affecting weight. And you know, some of this stuff you might have access to, but in many cases it may be very difficult to obtain information on a lot of these variables. And you know, we went through this list very quickly, but can you imagine what it would entail to come up with like a comprehensive list of all these things, right? We can easily miss something, even amongst the, you know, 20, 30 of us here, listing all these factors. Who's to say that we're able to identify all of the factors that affect weight, right? So, what the fixed effects does is it tries to, it attempts to essentially group these things into a measurable category. And so, what I will say is that some of these variables that you guys listed as examples are gonna be like ever so problematic for what I'm about to say, but let's assume that all of these things are kind of just related to the individual and don't change over time. Okay, and so what I mean to say is that specifically diet, medication, and stress, let's assume for a second that those will be different between individuals, but that they don't change over time. Okay. So that would, if you accept that assumption, that allows us to do something like this. We can now change this chart to look something like this. Individual factors. Okay. Where individual factors captures everything specific to that individual. Okay, so we can call all of these variables as individual factors. Oh, sorry. Not this again. Okay. So one way that I'm going to try and visualize this is let's draw this in kind of like a table so we can see what this looks like. So let's suppose that I have an index for an individual I, and then we observe something over time, T, weight, exercise, and then we observe things about the individual, so like race, gender, height, genetics, and I'll put one of the, what did we say? Oh yeah, like diet, and so on. Okay. So let's say for individual 1, we observe several time periods, and we observe differences in their weights, ABC, differences in their exercise, DEF. Okay. For the race, it's actually just going to be the same, right? U1, U1, U1. For gender, it'll be the same, V1, V1, V1. Height is going to be the same. Genetics, something like this. And again, for now, I'm assuming that the diet is basically the same, okay? And really, you're seeing something like this, right? There's like a little subscript I, and then for weight, you have IT, and exercise has I and T. So for individual 2, it might look something like this. GHI, JKL, okay, U2, and for the rest of these, they're going to be the same for this individual. and so on. And for individual 3, I'll just do this really quick. M, O, P, Q, R, U3, okay. Everyone following along so far? So, we would want to control for all of these things, right? Because we know that these things influence weight. But in fact, if you observe the fact that these things are fixed across a particular category, of which we're calling, right, an individual, then actually controlling for your individual lets you control for all of these things. And in fact, more than that, right? Any of these things that we didn't talk about, that we missed, any information about those variables would automatically be captured under the individual factors. Okay, the only things that wouldn't be captured are things that vary in both I and T. Okay, so in this particular case, this is almost like an experiment in the sense that if you have a whole, if you're serving a large group of individuals and you can observe how their weights change as their exercise changes, which is what we see in these two columns, you actually don't need to know anything about all of these fixed things that are related to the individual, like their height, like, you know, the city that they're born from, their race, their gender, all of that stuff is sort of automatically captured by this individual factor term. Okay, so all of these are same or individual I, and are fixed effects captures this plus all unobserved terms. That don't change over time. Okay. Any questions about this so far? So there are kind of like two ways that are commonly done to actually execute a fixed effects. And so let me show you the equation and then let's talk about how they're kind of applied to this particular example. Two ways to do this. Commonly, I should say. So one, D meaning variables by extracting within variation. So this is yit minus yi hat is equal to beta 0 plus beta 1 xi Okay. So this looks a little different. So what is going on here? So our regular regression equation kind of leaves out these parts, okay? But essentially what you're doing is we're doing this process called demeaning. And the way that you can kind of qualitatively think about this is that when we're thinking about this, okay, I'm gonna leave it all in here. What you're kind of saying is that, okay, I'm gonna treat, blue as this individual, and that individual is gonna be of some average weight and some average exercise, and the difference in that average weight and exercise, we're gonna subtract away, let's say all of these other things that might affect their average weight, and so that you're only concerned with essentially how their weight is changing as affected by how much they're exercising. Okay. So procedurally what I'm doing here, yit minus this part is, I'm taking a regression equation that's gonna do a minus a plus b plus c over 3, b minus a plus b plus c divided by 3, and c minus a plus b plus c divided by 3. So I'm subtracting away the sort of average weight that I'm observing over different exercise regimes. Okay, and same with this thing. The thing that you're demeaning is the variable you're interested in that has this causal thing, and so I'd be taking out the average effect of all of those individual factors on exercise as well, and demeaning that. So it would be d minus d plus e plus f divided by 3, and so on. Okay. Any questions about this? So the second way to do this might be slightly more intuitive, but I will say that this is the way that is usually suggested you approach this in some of these causal tasks, because really I only care about this beta, which is the causal effect of exercise on weight. But they will actually end up being the exact same answer. So 2 is add a binary control variable for every individual. So yit is equal to beta 0 plus beta 1 xit plus beta 2, let's say d where I equals 1 plus beta 3 where d I equals 2 plus beta 4 d I equals 3, and so on and so forth. Okay, so this method here is where I have a dummy variable for every individual. Okay, so I would have in my table d I equals 1 would be 1 1 1 0 0 0 0 0 0 0. d I equals 2 would be 0, 0, 0, 1, 1, 1, 0, 0, 0, and so on, right? So this is the alternative way of doing it, where you just add a dummy variable for each individual. And if you do it this way, you will find this beta 1 is exactly the same as this beta 1. I think maybe this is easier to interpret, at least in the sense that we've seen this type of thing before, right? And so we kind of have a better understanding of interpreting this, but I will say this is a lot more rare to do it this way, especially because you may have many, many individuals. And like, do you really care about these coefficients? Probably not, right? If you're doing causal inference, really what you care about is this beta 1 effect. Okay. Yes.
It's a little bit confusing. What does beta 1 tell? I mean, what is the xit? What is the x?
Yeah. So.
What is the x is exercise?
Sorry. So weight IT and exercise IT. That's just telling you that the weight will change by individual I, and it also changes over time. So here, right, I have I's and I have T's, and this is kind of an indication that weight varies both over time and by different individuals.
So the x is exercise.
Yes. So that the equation is a generic thing, but in the example, right, you can think of this as exercise IT minus the average exercise for that individual. So this would be exercise IT minus exercise I. So it is the average amount of exercise happening for the individual.
And then when we talk about the dummy variable.
Oh, sorry, this would be for here, not for Y.
So when we talk about the dummy variable, so for example the beta 2
Yes,
dummy variable,
these guys.
are we talking about the rates or?
No. So dummy variables would be, in this case, something like di equals 1 would be 1, 1, 1, 0, 0, 0, 0, 0, 0. Di equals 2 would be 0, 0, 0, 1, 1, 1, 0, 0, 0. It's a dummy variable for the individual I. Yeah. Yes.
So we talk about fixed events capturing hormones of drugs. Right?
Yes.
So beta also does the same.
Kind of. Except that you can imagine that these dummy variables, that the fixed effects are more powerful because they are capturing all of the effects associated in a particular category, right? And so beta 0 would not capture variation happening across I's, whereas your dummies would. And in fact, that's actually a huge thing because, right, that's the difference between letting me capture all of this stuff versus not capturing any of it at all. So if diet were also changing over time, then that would not be captured in our fixed effects, and that would actually fall out. Okay, so if diet was not Z1, but it was, you know, other letters, I'm out of letters, Z, AA, and AB, right? Then this dummy term for here would no longer capture the variation. Sometimes I really hate this thing. Okay, so if that were the case, then you would no longer if these were different values, then the dummy variable would no longer be capturing that variation, and now this is having effect on my weight again, and I am no longer controlling for it. So then I would need to like control for diet again. So it doesn't totally solve this problem, right? Where we may have other variables, or we have variables that are hard to control. But anything within the individual factors group would be controlled for as long as they're not changing across a different category. If they are, then we would need to control for it. Okay. Questions about this? Okay. So this is actually a very powerful tool, very commonly used in causal identification when you have the opportunity to do something like this. It often does let you, I mean, you still have to justify some of this stuff, but it often does provide kind of enough ammunition for you to argue that you are getting a causal effect, right? Because a lot of the things that you wouldn't be able to account for kind of automatically get clumped into your fixed effects. Okay. Okay, so let's take a look at how to do this. One moment here. Okay. So we are going to load a data set from the causal data library called Gapminder. And let's take a look at this. So we have the country, continent, year, life expectancy, population, and the GDP per capita. What I would like to do is to have some understanding of how the GDP per capita relates to life experience. Okay. So this is using, we're actually going to use some pipes. So this is a way of manipulating data in dplyr, which is part of the like tidyverse environment. If you guys recall from the R tutorial days, I was saying how I use data tables and not dplyr, but these examples are using dplyr, so it's going to be a little bit different, but I will walk us through what's going on here. Okay, so we're going to put GDP per capita in log format since it's very skewed. So just a little bit of data manipulation. So all this is doing is creating the new column called log GDP per capita, which is the log of that column. And then I want to perform each calculation by group. So group by country. So in this particular example, instead of doing groups of individuals, I'm actually doing groups of countries. And then I want to get within variation by subtracting out the mean, right? So this is our demeaning process. So I'm going to create a variable that's demeaning the life expectancy. I'm going to create a variable that is demeaning the GDP per capita. And then we no longer need the grouping, so ungroup. So this is a little bit of data manipulation. So all this is doing is creating the demean variables. Okay. Hopefully everyone is following along, and let me go up here and run all of this. Oh, I did not. There we go. So now if I look at the data, I will have log GDP per capita, that's the first thing, and then I will have these two new columns, which are basically taking So log GDP per capita within, that is taking this column here, taking the average in each country and subtracting it from the value. Okay? So let's run our regressions now that we have everything prepped. So analyze the within variation, M1, life expectancy within as a function of log GDP per capita within data equals GM. So I didn't actually know about this M summary function until recently, but this lets you do kind of a cleaner, more econometric looking style table. See what it looks like in just a second. Okay, so our regression, just a regular old linear regression where we've manipulated the data to demean everything so that we're essentially running a fixed effects. And let's see what happens. Okay. So let's see the whole thing. Okay, yeah, there's a couple more things here. Okay, but anyways, this is now telling us essentially, after including all of the fixed effects, what the log GDP per capita, how that translates to differences in your life expectancy. Okay, and so yes, I will probably need to go a little bit farther to argue something like causality, right? In this case, let me see here. So this is going across time. And so if we were to think conceptually, right, about like the causal model where I have GDP going into life expectancy, this is telling us the effect of the economy controlling for everything specific about the country, right? So I have now captured basically anything about the country that doesn't change over time. But, you know, if I wanted to argue causality, you know, I'd have to probably be a little bit more careful about making sure that there aren't specific things happening within the country that change over time that would be leading to changes in your life expectancy. Okay? Does that make sense to everyone? Okay. Let's look. Okay, and so the one additional thing to note, right, our interpretation of this would be something like, as the GDP per capita increases by like 1%, right, the average life expectancy would increase by almost 10 years, 9.7 years. So let's try to do this procedure where instead of doing the demeaning, I'm simply going to control for every country as a dummy variable. Okay, so this is analogous to what I was saying, that second procedure where we have all the dummies, the d I equals 1, d I equals 2, that is adding every country as a dummy variable. So, I'm going to reload the data. And my model 2 is going to look something like this. And let's just copy and paste this. Okay. So before I run the summary, right, we are no longer doing anything with the demean data. We're just doing it kind of straight up, but this time we have factor country, so we'll have a dummy variable for every single country. And this time, we now have a whole bunch of dummies, okay? So all of these are the effect of each individual country. So this would be something like, okay, let me see what the intercept country is, Afghanistan. Right, so do you guys remember how to interpret this, right? So if the intercept is substituting the baseline value for Afghanistan, then Albania on average would have a 10-year higher life expectancy than our 17-year higher life expectancy than the baseline of Afghanistan, okay? And so on. And let's scroll all the way down here, keep going. So we get to the end. So then the effect of the economy of the log of the GDP per capita, 9.769. If you guys remember, that number is exactly the same as in the model that has the demeaned data, okay? So again, you can kind of see more directly here, we are now controlling for everything unique about the country, unless there are things in the country that change over time, but we're controlling for all of that, and it lets us get to this same kind of conclusion. And part of why I said this model is a little bit less common to run, right, is because, okay, you have 230 extra dummy variables that you don't really needed to have generated in the first place, okay? And you can imagine a fixed effects for, something like, if you have a panel of individuals, if you have a panel of 1,000 individuals, are you really going to generate dummy variables for all of them? And are you really going to interpret every single one of these coefficients in your report or research or whatever, right? The fact of the matter is that these dummy variables, these are controls to get at that number. And so it is much more common to do the first method where we're not including everything. Okay, any questions about this? So, hopefully, I'm hoping you guys can see kind of how powerful of a tool this can be. And in fact, the nice thing about fixed effects is that you can kind of layer in multiple groups or multiple panels, right? And so in this particular example, we're just showing what's known as like a one-way fixed effects, where you're just controlling for all of the variation within one group. But I can do that for other groups as well, right? Is there another group from this data set, even from this small data set, that we could leverage? Any variables in here?
Maybe population.
So population, population is changing across multiple groups, right? Because it changes by country, but it also changes by time. So that would be trickier to do. But I kind of just said it, right? The one group that you could do is time itself, right? So by controlling the within variation of the countries, I control for all the countries. I can also control for groups by year, and so you control, it wouldn't tell you anything about something particular happening within a country within a year, but it could tell you variations across time that happen to all the countries, okay? And so let me show a way of doing this in a more simplified way that pertains to one-way fixed effects too. Because what we did is kind of a little bit more manual. The way that this would be done would look something like this. So two-way fixed effects, we're going to use a function called FEOLS, which stands for fixed effects OLS, ordinary least squares. And we can just run our regression kind of as before. But now you add the fixed effects like so. Okay. Wait. Oh, I have an extra. Wait, okay. So here, the way that you're adding a fixed effects is you have this vertical line, and then you add in the group, each group that you want to treat as like one of your fixed effects. Oh. Yikes. Okay. And when you do it with the FEOLS, it's a little bit easier. You don't have to do the demeaning of the data yourself. The function will actually do it for you, and then it gives you the results without all of the dummy variables. And in this case, we are controlling for two fixed effects, both the country and the year. Okay? All right. Any questions?
How the 1.450 will be interpreted in this model?
Yeah. So so I would say this model is a little bit more robust than the last one. In this particular example, or in the last example, we were seeing like the 9.7, right? So it would say, as the strength of your economy increases by 1%, right, your GDP per capita, then life expectancy increases by 10 years. Well, you can imagine that actually there are things happening within the country over time that don't relate to the economy, but may still improve life expectancy. So what would it be an example of this? Let's say, hypothetically, let's just say you've got you're in a country with a particular type of disease, and like a new medicine comes out that cures that disease, and it gets introduced into your country. It doesn't really affect the economy, but it improves life expectancy. So this might be a change that happened over time that wouldn't be really observed within the country variation, but would be observed over time. And so this second model controls for that second thing, and for a whole bunch of other unobserved things that happen over time. So anything that happens over time that you aren't able to control for, that's not unique to a country, would be captured with this effect. And so the new interpretation would be, okay, when I control for all of these changes that are happening over time, well then the actual change in life expectancy as economy increases by 1% is a 1.45 year increase in average life expectancy. Okay.
Would you say the second model is a more realistic understanding of
Yeah.
the data?
Yeah, because there's probably examples of things that are changing over time that wouldn't be captured in your within country variation. So it's like things that are affecting life expectancy in the country that's not related to the economy. Yeah. Okay. So that is our first example of a tool that we can use. And let's go to a different example, or a different tool. Okay. We are going to look at really missing it. Okay. Differences in differences. So this is a method of controlling effects by observing groups undergoing treatment versus groups that never undergo treatment. So something like this. So treatment going to outcome. And you have something like time. And group. So adding group adds a backdoor. So if I isolate within variation for treated and untreated groups, then I closes the back door. To compare variation in treated group to within variation in untreated group. Controls for time differences. And closes the back door. Okay. What does that mean? So let's look at an example of this, and actually I think this will be a lot clearer. So the example that they give in the that causal book that I was talking about, that I'm drawing this material from. So this relates to an infectious diseases example. So back in the 1800s, a bunch of people in London would get cholera. But unlike now, kind of an understanding of where that illness was coming from was, let's say, a little bit less known. And there were a series of investigations on sources of the disease, one of which was from like water sources. So we actually know now, right, that like dirty water can lead to propagation of bacteria that could lead to getting cholera. And unfortunately at the time, like there was a lot of water sources in the city where you could upstream, you would have, dirty like feces and stuff like that kind of interacting in the water and leading to those bad outcomes. So there were two areas in London. So London area 1 and London area 2. Okay, so time equals 1849. And I can make some observations from data about the death rates in these two areas. So death rates in 1849 versus in 1854, and oh my god, I have area 1, area 2. So something like this. And if you look at the data, might look something like this. This is, I think, deaths per like 1,000 or 10,000 people. I know that makes a big difference. I can't actually remember which one. Okay, but there was something unique that happened in here. It's called the Lambeth intervention. So this was something that happened where the water source, so shift in upstream water source. Okay. So this is an intervention that changed where the water was coming from in one area, but it didn't happen in the other area. Okay, so then was there a difference in cholera? And here there's no treatment. So this is Lambeth, and this one is non-Lambeth. 130.1 and 84.9. Okay. Oh wait, sorry. I have it backwards. This is area 2, this is area, okay, sorry, one second. Okay, now that makes more sense. Area 2, area 1. So, right, one question that we might have, right, so there's inherent differences in the death rates between area 1 and 2, right? And so how can we say or know that an effect that's happening, over time isn't something like particular to one of these areas? And so you have to understand that like this differences in differences method is strictly about trying to find right this effect that's attributable only to some kind of like treatment. And so hopefully you guys can see the intuition here, right, is that if I didn't have area 2 and I only had information about area 1, I might not be able to isolate changes in death rates over time specifically to that treatment effect, right? But the argument is essentially, well, any of those changes that are happening over time that might be increasing or decreasing death rates, those should be reflected in my other areas. And so the only difference between multiple areas is that treatment. And as a result of the treatment, I can kind of estimate the specific effect of that treatment on the death rates, right, that are, we now know are coming from like cholera infection. Okay, any questions about this? Okay, so I'm gonna go. So the way that we do this, so y is equal to alpha g, alpha t plus beta 1 treated plus epsilon. And actually, with two groups, you get the same. So this equation ends up being the same thing. Beta 0 plus beta 1 treated group plus beta 2 after treatments plus beta 3 interaction treated group times after treatment. Okay. Does this equation look similar to anything that we've talked about today? So that is actually the same thing as the two-way fixed effects. So differences and differences, mathematically, right, we're conceptually thinking about this slightly differently with this framework, but mathematically it ends up being, you can represent it in the same way as doing the two-way fixed effects. Okay? So, let's show how to do that here. Okay, so we're gonna do difference in difference example. So we're gonna use a different data set. We're gonna look at a data set called organ donations. So all this tells us is the state, the year and the quarter, the organ donation rate, and the quarter number. And that is, quarter number is just it's just a representation of time, okay? Because we have data from Q4 of 2010 through Q1 of 2012, and so it's saying in the data set we're looking at the first period, second period, third period, and so on. Okay, so this is just a quantified version of our time. Okay. So this data set was actually meant to answer a specific question about changes in organ donation rates resulting from a state level policy that mandates organ donations. Or not, sorry, not doesn't mandate organ donations. So who has a license in California? Most people. So when you get your license, it used to be that you can choose to become an organ donor, and then they like put it onto your license card, and it's an opt-in procedure, but in the third quarter, in the summer of 2011, California policy changed, so it's an opt-out procedure. So you are automatically an organ donor unless you check opt-out, where it used to be the reverse before. So the question is, did that policy lead to sort of more organ donations, once it was implemented? So that's our treatment, right, is a change in policy. And, California did this, but other states didn't, and so we have all of the sort of necessary conditions to do differences in differences, because we have groups that were treated and we have groups that weren't treated, right? In the same way that in the London example, we had some areas that were subject to the Lambeth intervention and some areas that weren't. And so we can do kind of a similar type of analysis here. Okay. So first thing we need to do is we need to indicate the treatment. So treatment variable, and I'm going to create a new column in OD that's called treated equals state equals California and quarter in Q3 2011, Q4 2011, Q1 2012. Okay. Right, and so there's gonna be this new variable called treated, which is true when you're in these time periods. Okay, so those are the time periods in the data where the treatment was applied. Okay. And now we can just run our two-way fixed effects. With the groups being state plus quarter. Okay, one sec. Okay. So this will essentially allow us to run this differences and differences model. So this ends up being kind of the same thing as a two-way fixed effects. And let me grab one of these guys here, copy and paste here. Okay. So again, kind of analogous to the London example, we know that, you know, organ donations might fluctuate a little bit over time, right? And we want to make sure to be taking advantage of groups that aren't treated to control for that variation over time, so that hopefully we can really get at the causal effect of the treatment. In other words, the opt-out procedure for organ donations on organ donation rates. And so what do we see here? What does this tell us?
It didn't increase.
Yeah, in fact, it went down, right? And so in states that put in an opt-out policy, in other words, just California, when that treatment is applied, we actually observe organ donation rates going down. So this was actually something that did happen. And maybe it's a short-term effect, right? These are only 3 quarters. Some people say, you know, this could be when the news comes out about something like this, people are more vigilant about actually opting out. But yeah, in this particular case, the treatment effect might be a little bit counterintuitive to your intuition, but we do observe in the data, right, that there was a decrease in organ donation rates, and that we are fairly confident that those aren't just attributed to like random fluctuations in time, because we are observing those random fluctuations happening in other states as well. Okay? Any questions about this? Yes.
So you said this only really is effective when comparing one treatment, you can't do multiple treatments at the same time?
So the trick is, for any individual treatment, you would want to be able to observe variation in outcomes relative to like all the data that you're having. So if I had a treatment effect happening in California and a different treatment effect happening in Nevada, I would not be able to do that, right, if they're happening at the same time, if I don't have information about other states, if those were the only 2 states. But if you do have information from the other states, right, then you could still make conclusions, right, because the average effect of like time would still be controlled for in the other states, and you might observe a different effect between one treatment in California versus one treatment in another state. Similarly, this is in a very analogous way. If I have a treatment effect in California in time period like 5, and then I had another treatment effect in California in time period 10, then I have some data about what treatment 1 was doing, like over even controlling for time, and then I would have another, once the other treatment effect kicks in, then ostensibly you would have more data about what that treatment was doing. So that is analogous to the California and Nevada example, where instead of observing between state variation, you're observing like between time variation. In both of those cases, you would be able to do multiple treatment effects. Now, the one that wouldn't work, right, is if you weren't able to distinguish how that variation was affecting an outcome. So if I had 2 treatments in California at the same time, then I don't really know if it, so if you have 2 treatments happening in California at the same time, even with the other states and even across time, like I wouldn't know if it was treatment 1 or treatment 2 that was leading to a particular outcome. So, yeah, long answer, right? But yes, I can look at multiple treatments and differences. And here, right, you could have like treatment 1 plus treatment 2 plus treatment 3, and then still controlling for these things, and you would be able to observe the differences in those treatment effects unless they were happening without variation in here. Okay, because then I wouldn't know which one was the thing that was leading to an outcome. Does that make sense? Does that make sense to everyone? Yeah. It would be like, I don't know. If everyone in the class was sick and then I gave one person an injection and they got better, then you could tell the difference. Or if I gave, you could do multiple treatments, right? I could give a couple people different injections and then see which ones get people better. But if I gave someone 2 injections at the same time and they got better, I wouldn't know which one was the thing that fixed them, right? That's kind of the idea here. Okay. Any other questions? So yeah, kind of big picture thing, backing up, this fundamentally goes back to that problem I was talking about last time in our causal identification, right? In our causal thing, right, at the beginning of class, we said, oh, what are all the things that could affect your weight? So many things, right? What are things that could affect death rates in London? What are things that could affect organ donor rates, right? So many things could affect that. But the power of these fixed effects and the power of the differences is that it lets us like broadly control for all of these variables kind of all at once. That's really the power behind this. And yeah, these are very common tools that are used in identification because, you know, we can qualitatively argue that a lot of the things that you would need to control for are kind of automatically accommodated in these like groups of controls. Okay? All right. Last one for today. Okay, we'll jump over here. Okay, while differences in differences is like intimately similar to fixed effects, we're going to look at a pretty different type of approach now. So this is a variable that affects your treatment and affects your outcome only treatment. Okay, so the idea is this can remove any part of the outcome that is not explained by the instrument. So the idea is something like this. X going to Y, and you have a ton of unobserved variables. So in this example, so let's go back to our original thing. So it was exercise, weight, and we talked about how you might have lots of unobserved variables. Okay, one of these things might be something like die. Okay. Okay, so the argument might be something like, if I do a lot of exercise, right, then my weight might go down. But maybe, someone who is motivated to lose weight is both dieting and doing a bunch of exercise. And so the weight changes, the exercise is changing, but the diet is also changing. So it's very difficult for me to ascertain the specific effect of exercise on weight. Okay? Or it could be something like you're eating a lot more so that you have more energy to exercise, and the eating more increases the weight, but your exercise decreases the weight, and so at the end your weight doesn't change, and you don't know how diet and exercise individually might be affecting weight, right? Hopefully we can all see this. So what if we could find a way to affect exercise without affecting anything else? Then we could observe a particular change in exercise, and then thereby looking at how weight changes when we control for all of these other things. So that is what an instrumental variable is meant to do. So IV goes like this. So the IV, or the instrumental variable, is very particular, right? It has to only affect the outcome through the variable that you are interested in. If there are any other connections, then it is an invalid instrument. So you cannot have this, you cannot have this, these are all no good, you can't do something like this. Those would all make these things invalid. Okay, So in this particular example, let's say you observe someone, you observe their exercise and you observe variations in exercise and you observe variations in diet and you observe variations in weight, but we don't know how these two things individually are affecting weight. So I'm trying to think of like an instrumental variable kind of on the spot. So what might be something that affects your exercise without affecting your diet? So let's say it's doctor's orders. Okay, so let's say the doctor says, okay, like don't change anything about what you're doing, just like continue doing what you're doing, but add in 30 minutes of exercise every day. Okay? So this would be an example of an instrumental variable in the sense that I could, the doctor just like telling me to do something probably isn't gonna change my weight, right? Like someone speaking to you doesn't like cause you to lose weight suddenly, right? And so we can be kind of certain that this is not happening, okay? And they're not telling you to like change your diet or anything. In fact, they're saying like don't change your diet, keep doing what you're doing, just change your exercise. And so there's no thing that's happening here. So in this example of the instrumental variable, you might change the amount that you're exercising a little bit, and then we would then observe how that would affect your weight once you're like controlling for all of these other things. Okay, and so there's actually a very specific procedure that we can use to estimate this. So this is called two-stage least squares. And the way this works, so in our regular one, OLS is something like this, right? Y equals beta x plus this. So it would be stage 1 is your instrumental variable stage, where I do x equals IV plus, I think they use this variable. Okay. So in the example here, our first stage would look something like this. Exercise is equal to delta doctor's orders plus beta 2 or delta 2 times diet and then stage 2 would look like this. Oh, actually before I write that. I want the prediction of x given my instrumental variable. So stage 2 will look like this. Y equals beta so note the difference, right, is that instead of putting in my x here, so this x being exercise, I'm gonna essentially put in the exercise as predicted by this first stage equation. And if you think about this conceptually, what it's doing is it's basically saying, look, I know that there's all these unobserved things like diet that are affecting the weight, but I am going to only measure how IV changes exercise leading to weight changes. Okay, and so this lets me isolate that effect by looking at predicted X as a function of my instrumental variable. So this is one of the most common procedures and most powerful procedures for getting causal effects, because now I can confidently say that the exercise effect on weight, like this beta, has essentially isolated itself from all other changes in, or isolated the effect on weight from variation in all other variables. Okay. This again goes back to the reason why this is really powerful, right? Is again, literally doesn't matter how many other variables are going into here, right? And that they can be unobserved stuff, but this lets me isolate the effect of exercise. Okay? Questions? Okay. Why don't we actually do the IB example pickup at the beginning of class next time? Yeah, that way I don't cram it in the last couple minutes and we have time to digest. Okay, so I think we'll end here for today, and we'll pick up where we left off, doing example in R of IB regression.